Welcome to Properties of Integers. The topics we will cover in this video are induction, recursion, and a quick introduction to integer division. A following video, part 2, will be a more complete coverage of integer division and division algorithm, as well as bases, the Euclidean algorithm, and the fundamental theorem of arithmetic. We will start with induction. We start with the well-ordered principle. Any non-empty set of positive integers contains a smallest element. The well-ordered principle does not apply to all sets. For example, the set of complex numbers. Given a set of complex numbers, we don't really compare and say one is smaller than the other. So in this case, the well-ordered principle applies to positive integers, which we will be using in induction. The finite induction principle, also known as the principle of mathematical induction, says, let S of n denote an open mathematical statement or set of statements that involve one or more occurrences of the variable n, which represents a positive integer. Then if the base case is true, if S sub 1 is true and the inductive hypothesis is true, and this is the inductive hypothesis, if whenever S of k is true for some particular but arbitrarily chosen k, a positive integer, then S of k plus 1 is true. Again, the inductive hypothesis is essentially if whenever S of k is true, then S of k plus 1 is true. Then, if these two things are true, the base case and the inductive hypothesis, we can conclude S of n is true for all n, where n is a positive integer. Here is the finite induction principle restated, and the proof is based on the well-ordered principle. It is outlined, let S of n be an open statement satisfying the base case and the inductive hypothesis, and let F be the set T of all positive integers such that S of t is false. So assume that F is not the empty set. Then by the well-ordered principle, F has a smallest element. We'll call it S. Since S of 1 is true, that's because the base case is true, right? It satisfies the base case. S is not equal to 1, so S is some number greater than 1, which implies S minus 1 is a positive integer. With S minus 1 not an element of S, we have S of S minus 1 plus 1 is true by the inductive hypothesis, which is a contradiction since S minus 1 plus 1 is S, but S is supposed to be the smallest element that does not, where S of t is false. Don't worry too much about this proof, but I wanted to give you kind of an outline and so you can see how it's based on the well-ordered principle. It depends on having a smallest element S. I do plan to discuss this principle of mathematical induction to give you a better feel for what's going on, but first I want to show you an example, another way of giving you a feel for what's going on. So the example we will look at is prove that 1 squared plus 3 squared plus ... some odd number squared is equal to n times 2n minus 1 times 2n plus 1 divided by 3. And here is the principle of mathematical induction just to remind you what's going on. But essentially, if we want to prove this formula here, we're going to start with a base case. So we want to show that S of 1 is true. To show my base case, I need to show S of 1 is true. So I plug 1 into my formula. So I'm going to add all the numbers up to 2n minus 1. If I plug in 1 here, 2 times 1 is 1 minus 1 is 1 squared. So basically I'm just adding 1 squared. And then I plug in 1 here, I plug 1 here, and 1 here. So this is 1 times 2 minus 1 is 1. 2 plus 1 is 3 divided by 3. So that also gives us 1 on the right hand side. So the base case is verified. For the inductive hypothesis step, we're going to assume this is true for S of k, and then we are going to show it is true for S of k plus 1. So here I've written out my S of k. So basically I'm assuming 1 squared plus 3 squared up to 2k minus 1, that should be a squared, is equal to k times 2k minus 1, 2k plus 1 divided by 3. So I added in my squared term there. My next step is to show for nk plus 1. So I wrote this out, 1 squared plus 3 squared. I did write the kth term, and you'll see why in a minute. And then I wrote my k plus 1 term. So I plugged in n equals k plus 1 squared equals, and then on the right-hand side, I plug in k plus 1, my k plus 1 here, 2 times k plus 1 minus 1, 2k plus 1 plus 1 divided by 3. Since we're doing induction, at some point, you're going to have to use your inductive hypothesis. If you write a proof without using the inductive hypothesis and you're doing a proof by induction, then something's gone wrong. So this is the point where I am going to use my inductive hypothesis. So right here, this is why I wrote the first k terms and then I add the k plus 1 terms, because my first k terms I could apply my inductive hypothesis to. So by the inductive hypothesis, this here, and I abbreviated inductive hypothesis as IH, is equal to k, 2k minus 1, 2k plus 1 divided by 3. So here I plug in my inductive hypothesis for my first k terms. I bring down my k plus 1 term, and I also simplified it some. I also did some simplification over here on the right-hand side. And the rest is algebra on the left-hand side until my left-hand side equals my right-hand side. And thus I had proven, there needed to be a divided by 3, but thus I have proven my, my formula. And again, the steps are the base case, you prove for S of 1. You assume the inductive hypothesis, you assume for S of k, and then you show for n equals k plus 1. During this step, when you show for n equals k plus 1, you must use your inductive hypothesis. You can't just say, oh, the rest is algebra, because it's not. You have to plug in your inductive hypothesis, and from there you do algebra in order to prove the left hand and the right hand side are equal. I did say I would say a word about induction. The thing that I thought when I first learned induction that was really strange is this assumption that you assume for S of k. So it seemed to me that really you assumed exactly what you were trying to prove. It's just that instead of n's, you replaced it with k. But it really didn't make sense. It seemed very suspicious to me. So I had a professor of mine, Dr. Spur, had explained this to me so that it would make sense to me. So he basically said that induction was like a ladder. And this ladder is a special ladder. But the things he could tell me about the ladder is, one, that I could climb on the first rung. That was like a base case, being able to get on the ladder, having a place to start. And then he said, okay, once you have a place to start, the base case is established. Then he told me, well, once you're on one rung, you can always climb up one higher. You can always reach the next rung. That's the inductive hypothesis. He's telling me, okay, if you can get to S of k, then you can get to S of k plus 1. Then what he told me is, if you know these two things, that you can start on the ladder, and once you're on one rung, you can climb to the next highest one, then basically what you can conclude is that you can go all the way up the ladder. So that's what induction is. We have a base case, a place to start. We have a way of going up one step. And then from there, we make the conclusion that we can go up all the steps. So hopefully induction won't seem too suspicious to you. Another example, I like this one because it's quite a clever proof. I think it's a Euclid proof. But basically, prove there are an infinite number of primes. So he starts this proof by saying, my S of n is the statement there are at least n primes. We need a base case, a place to start, S of 1, so there is at least one prime, and that's the number 2. You could put out any prime number you wanted. I just chose 2. We have our inductive hypothesis. We're going to assume for n equals k, in other words, S of k. there are at least k primes, and we will call them p1, p2, all the way up to p sub k. To show for n equals k plus 1, in other words s of k plus 1, we're going to consider our k primes. And the k primes we get from our inductive hypothesis. So this is where we're using our inductive hypothesis. We assume there are k primes, then we consider multiplying all the primes together and then adding 1. So this number here, the sum, is either a new prime or it can be factored into prime divisors at least 1, which is not p1, p2 up to pk. So, and that way we've gotten another prime divisor or more. So just to be clear, this algorithm does not necessarily give you the prime divisors in order. So for example, so just a word is this, this algorithm does not necessarily give you the primes in order. So for example, if P1 is equal to 2 and P2 is equal to 3, then this algorithm, when you multiply P1 times P2 plus 1, you get 7, which is your new prime. But you'll notice you skipped over 5. Another example, if P1 were equal to 3 and P2 were equal to 7, then P1 times P2 plus 1 is going to give you 22. So this number is not a prime. However, this part is it can be factored into prime divisors. So this can be factored into 2 times 11, at least one of which is not our P1 or P2. So that's 11. 11 is your new prime. So in this way, he's shown you that there is a place to start, and once you have a place to start, how to get another new prime, and from there you can keep adding primes until basically you are at any number you want. Now we're done with induction, and we're ready to go on with recursion. Recursion is used when an explicit definition of a mathematical concept, such as a set, binary operation, a function, or later in Chapter 5 we'll see language, is difficult, so we define based on prior results. Our first example is a familiar one, the Fibonacci sequence. So we have f naught is equal to 0, f1 is equal to 1, and then f of n is based on our last two prior results, where we add them. Another example, sometimes when you have an explicit formula, you can come up with a recursive definition as well. If you are asked to guess and then verify a recursive definition for an explicit formula, there's no set instructions for how to do that. It's kind of an art. But one thing I can suggest that you do is make a table of small case analysis. You look at n, you look at your formula, and then you try to find a pattern. So in this case, you're looking for n squared. So when n is 0, it's equal to 0. When n is 1, it's equal to 1. When n is 2, it's equal to 4. N is 3, it's equal to 9. You continue with this table, and you try to look for a relation between these numbers and n. When it comes time to get a definition, you want to start with the base case, which isn't difficult at all. Guessing the formula is more difficult, but here I've come up with the formula that c of n plus 1 is equal to c of n plus 2n plus 1. I do a couple of test cases on the formula, so I plug in c2, which is equal to c1 plus 2 times 1 plus 1, so that's equal to 4, so that looks good. I have c3 is equal to c2 plus 2 times n plus 1, and that's equal to 9. When I want to go more formally and give a proof, recursions are tested quite naturally using induction. From our last example, where we were trying to get a recursive definition for the explicit formula Cn is equal to n squared, I had my base case. I had a guess at a formula. Now to actually prove the formula, again I start with the base case, so you can actually just start with c1 equals 1. Some people feel more comfortable doing another base case, and that's fine. So C2, you can plug in C2, and that's equal to 4. So far, so good. We continue with our inductive hypothesis where we assume for n equals k. In other words, we assume c sub k is equal to k squared. Now we need to show for n equals k plus 1. So we plug in k plus 1 for n. And here we get c sub k plus 1 is equal to c sub k plus 2k plus 1. But by our inductive hypothesis, c sub k is equal to k squared. So I substitute k squared for c sub k. And a little bit of algebra gets me k plus 1 squared, which is exactly what I wanted to prove. So here, I am done. Another example of when a recursive definition can be used, we have develop a recursive definition of multiplication of n real numbers, x1, x2, all the way to xn, where n is greater than or equal to 1. So it is most likely obvious to you how to multiply n real numbers now, but you have to go back and think about when you first learned how to multiply. It may not have been obvious to you how to multiply 2 times 3 times 4. You would have known how to multiply 2 numbers at a time, but maybe 3 numbers might have been a little more mysterious. Recursively, this is what we would do. We would start with the base case at n equals 2. Since n has to be greater than 1, our base case will be n equals 2. So if we have 2 real numbers, well, we know how to do that with normal binary multiplication. That's the multiplication you learned in 2nd or 3rd grade. The recursive part, now if we have n equals k plus 1, we're going to have our k and our kth plus 1 terms. But we are going to build our definition based on our previous results, our first k terms. So by associative law, I can group these k terms separate from my k plus 1 terms. But then I also know, because this is a recursive formula for the first k terms, I can keep going down until I eventually get to just 2. And then I add my last term on. So now we've done induction, we've just completed recursion. We'll introduce the topic of integer division in this video, and then the rest of the topics we will continue in part 2. Integer division. This chapter is about properties of integers. In particular, in the section we are embarking on, integer division, we want to stay inside the set of integers. We do not want to introduce non-integers by dividing, but it will be tempting at times to divide. But again, we must take care not to introduce a non-integer. To this end, we are given a definition of divisibility that will allow us to talk about divisibility without straying outside the set of integers. And here is that definition. If a and b are integers and b is not equal to 0, we say b divides a, and we write b divides a with this straight slash. If there is an integer n such that a equals b times n, we say b is a divisor of a, or a is a multiple of b. So this definition is our important definition that we use when we talk about divisibility. Our divisibility discussions will use this definition. We will not be doing the traditional dividing. We have a theorem that we will be using quite a lot. It's theorem 4.3. It's on your handout here. We can take a quick look at some of these parts of this theorem, and it should be familiar because it's about division, which we are used to. The first part of the theorem says that 1 divides any integer a, and also all integers divide 0. The second part says that if a divides b and b divides a, then a must equal to plus or minus b. Part C, if a divides b and b divides c, that implies that a divides c. D, if a divides b, then a divides b times x for any integer x. E, if x equals y plus z for some integers x, y, and z, and a divides two of the three integers, so it might divide x and y, or x and z, or y and z, then a divides the remaining integer. Part F. If a divides b and a divides c, then a divides any linear combination of b and c. That is, a divides any integer b times integer x plus c times integer y. And g is sort of a generalization of f, where now if a divides a number of integers c sub I, then a will divide any linear combination. This theorem is used quite often in this chapter, and you'll become quite familiar with it. To give you an idea of what the proofs of these theorems are and why these theorems are true, I will tell you part F, the linear combination one, where if a divides b and a divides c, then a divides any linear combination of b and c, is proved in your book. Part C, which says if a divides b and b divides c implies a divides c, I will prove for you here. My first step is to interpret these two given statements, a divides b and b divides c, and write out what it means according to the definition of a divides b and b divides c. So if a divides b, that means that there's some integer n such that b is equal to a times n. And if b divides c, that means there's some integer m such that c is equal to b times m. And again, my justification is that that's the definition of a divides b and b divides c. So here is an example where we're using that definition. So what I have is that c equals bm from this step here. And that I can say is equal to a times n times m. Just plugging in this definition for b. And I want to remind myself here m is an integer, and here n and m are integers. But now by associativity of multiplication, I can group my n and m, and now I know that m and n is equal to some integer. I didn't actually have to rewrite it, but this is an integer. And I know it's an integer because two integers multiplied together will give me another integer. Therefore, I have shown that a divides c. So now we've done induction, we've just completed recursion. We'll introduce the topic of integer division in this video, and then the rest of the topics we will continue in part 2. So now we've done our quick introduction to integer division, and we are done with this video. Our next video will go into further detail of integer division and continue with the division algorithm, basis, Euclidean algorithm, and fundamental theorem of arithmetic. Thank you for listening, and I'll see you in class.